Yeah, thanks, and hello everybody. I am Katrin. I am head of consulting at iWonder, and I'm here today with my colleague and data scientist Yuqiong, and we want to talk with you about chatbots today. Now, chatbots have received a lot of attention lately due to the release of ChatGPT. But also beside that innovation, there exists a variety of chatbots ranging from simple chit-chat to more sophisticated use cases, like the diagnosis of technical or medical problems. In our case, we wanted to build a chatbot for the retrieval of data as an add-on to an existing web app informing about the e-mobility infrastructure in Germany. So besides just showing the KPIs we regard as interesting to the user, we wanted to give them the possibility to extract exactly the data interesting for them. Hence, Yuqiong built a chatbot based on the Python Waza Framework, and she will explain now in more detail how she did this.
Yes, thank you. So before I really dive into the implementation details, I want to first talk about the big concept behind chatbot, and that is NLP. So we know that chatbot is just one application of NLP, and there are also many more other NLP tasks, such as sentiment analysis, where we detect the sentiment from a text, or we classify the text based on into the topics. And we also use translators every day to understand other languages, as well as auto-completion when we try to type words more quickly. And but behind all these tasks, there's something in common. That is, the machines need to understand the information that contained in the raw data, which whether it is text, a sound, or image, they need to all be converted into numeric representations. And this is the most important concept, I will say, in NLP, and I will come back to it shortly again. So now say we have such a sentence, electric cars are the futures. The first step we usually do is to get the tokens out of it. And there are many different ways to do it. The most simple way is that we use white space as delimiter, and in the end, we will get the tokens as individual words or characters. And a token is not necessarily a word, but it can also be a subword. And as long as we have the tokens, we can now think about again how we want to represent them. And again, there are also different ways to do it. Let's start with something more simple, like the sparse representations. So the typical sparse representations include one-hot encoding, where we generate a vector which has the same length as the length of the vocabulary in the text. And at the index where this word is located in the vocabulary, we will have a 1, all the other elements are zeros. And if we now want to generate directly our representation for the whole sentence, we can use the bag of words, which basically count the frequency of the words in the text. Now, we see that although these sparse representations are easy to understand and implement, they have obvious drawbacks. First, we have a lot of zeros in our representations, which means we need a lot of memory to store this kind of useful information. And this kind of representation is typically not so rich in the information it contains. It captures the syntactic information, but not the semantic. Therefore, we have to use the dense representations. And let's first have a look at the static embeddings. One of the most commonly used technique is word-to-vec, and it can be achieved by using 2 different algorithms. The first is SIBO, and the second is skipgram. And I want to here quickly explain how skipgram works. So we have, again, this sentence, and the core idea of it is we want to predict the context word given an input word. So let's say we have a window size of 1. We slide the window from left to right, and so for the first input word electric, which is marked in yellow, we consider one word before it and one word after it. In this word, we generate the training pairs. And after we get all these training pairs, we can train a shallow neural network to calculate the errors. And then what we care about in the end is lookup matrix. In this lookup matrix, each row represents a word representation for individual words in the text. During the inference, if we want to generate a representation for a word, we simply input the one-hot encoding of that word, and then we will multiply it with this lookup matrix. In the end, we get what we want as dense representations. And although static embeddings works quite well, but it does not take into consideration about the context. So in some situations, we will have examples like this. One word may have different meanings in different contexts. And if we want to have different representations for the word in different contexts, we have to consider using a dynamic embeddings. A dynamic embeddings usually uses a bidirectional structure while training, and then during inference, the way it works is by not putting the word itself, but putting the whole sentence. In this way, the model can capture the context information. Now, so far we have talked about the most important concept in NLP. I think it's time to have a look what kind of chatbots are there. So I have this classification based on this implementation of chatbot. And the most simple chatbot has a quite simple structure, and it is purely rule-based. This type of chatbot usually has a list of questions and a list of answers. And we match questions and answers using keywords. Rule-based chatbot is suitable for customer service and use cases where we have a limited number of questions. But if we want to now add more functionalities to the chatbot, it is not so optimal. But luckily, we have another solution for that, which can help us reduce the complexity when we define the rules. So that is our intent-based chatbot. So our intent-based chatbot first classifies questions into intents, and we only need to define answers based on the intents, but not for each of these questions. And our e-mobility chatbot that I developed is also our intent-based chatbot. So now, finally, I would like to explain how I implemented our e-mobility chatbot using Waza Framework. Here is a real example that I took from a conversation. So we know that in a conversation, we have a lot of turns. It can be from the user, and it can also from the chatbot. And for each of the user input, we will classify our intent for it. And in some cases, we also care about the small pieces of information that are contained in the user input. And so we extract the entities from it. In our case, for example, in the intent KPI query, we have to extract 3 different informations: the KPI, place, and time. And if we want to then use these informations later in our conversations, we need to use a slot to store them. From the chatbot side, every response is associated with an action. An action is where our business logic goes. It can execute events like as simple as generating a response, or it can also making an API call, querying the database, or setting a slot value. And afterwards, we have to also define stories for our chatbots, as well as rules if necessary. A stories is a bunch of intents and actions in order. This is a kind of abstraction where our conversation should look like. And rules is a special form of stories, but it is stricter, which means that the chatbot would always follow the rules first and then the stories. So after we defined all the necessary elements, we have to think about how we want to train the chatbot. Waza provides an NLU pipeline. So it is straightforward to see that when text comes in, we should first use a tokenizer to tokenize it into tokens. Then we use a featureizers to get the embeddings from it. In the end, the two main tasks for the chatbot is to classify the intents and extract the entities. And for each of the components in this pipeline, there are different options for which we can choose which model we want to use. And also, this pipeline is highly customized. For example, in our case, we want to also extract the name of the place, which is sometimes containing a umlaut. So I have to develop my own component for it, which is here, the rapid force anti-extractors for place. But in general, this pipeline can be adjusted according to our needs. Also, we have to train the model to train the chatbot to follow as policies, which tells it to choose which step it should take next. There are different types of policies. For example, the rule policies, which has the highest priorities. So the chatbot would always follow the rules if we define one. And the memorization policies tells the chatbot to follow the stories. So, but there are also hyperparameters that we can tune, for example, to let the model to be more generalized. Also, if both of these policies do not work, we can consider using a TED policy, which is machine learning based, and it will predict the next action based on all the information from the conversation so far, like the user input, the slot value, and so on. Now let's have a quick look at how our e-mobility chatbot looks like. Our chatbot is very user-friendly, so at the beginning, the chatbot will always greet the users, and it will provide a main menu where the user can choose which service they want to use. If they choose KPI query, then the chatbot will provide a list of KPIs which the user can query, and as well as examples how the users can ask their own queries. And then the user comes up with their own query, and the chatbot will get the information from the input and then query the database. In the end, gives back the response. Also, some users are extremely interested in knowing how many charging points are located around a certain place. So we also have developed this nearby search service where it's based on an overpass API, and so the users only needs to give the address of the search center as well as the search area's radius. Then the chatbot will display the address in text as well as gives back a map which displays where these charging points are located. Of course, our chatbot is also capable of answering e-mobility-related questions. And it is achieved by using a sentence transformer, where the chatbot has a knowledge base, and whenever the user asks questions, it will search the knowledge base and gets back the answer which has the highest probability.
So with this approach, we have built a chatbot which is successfully running and answering questions. However, we also discovered some limitations of our approach. And I want to start with intents here. So a main task for an intent-based chatbot is to detect the right intent. And that can be challenging. So here you see an example conversation of failure. The user starts with choosing the service e-mobility FAQ, hence the chatbot asks them, what do you want to know more about e-mobility? So far, so good. The user continues with asking which country has the most electric vehicles, which is a classic FAQ in principle. However, the structure of the sentence looks similar than sentences we have in our training sample classified with the intent KPI query, which leads to a wrong intent classification and hence to a wrong answer, and the conversation fails. This problem might be mitigated by a larger training sample. However, imagine all the questions users could ask. This might also be a challenge. Another thing with intents is that you lose contextual information. So in this conversation here, the user asks 2 times about the number of charging points in Berlin at 2 different dates, which is easy to answer. But the chatbot fails then afterwards when it gets asked to compare the 2 results because it does not know about the context of the last question. So these were 2 examples where we have challenges with intents, but I want to name 2 more things we face. The first one is about the training data. So if you have a domain-specific chatbot like our e-mobility bot, you also need domain-specific training data. And depending on the domain, this might not be available in a large number and hence can lead to some effort in collecting it. Second, we predefine the answers of the chatbot, and we also restrict the user in the way they can ask questions. This helps the chatbot to better understand the user and to react correctly, but at the same time, it also leads to kind of a robotic impression for the user. But there are also other ways how chatbots can be built, and I think it's time in the end to have a quick look at large language models and how they could maybe help us also with our issues here.
Yes. Nowadays, it's just not feeling so right if we don't talk about ChatGPT and large language model. But it indeed gives us also some inspirations how we can improve our chatbot. So let's start with the definitions of large language model. So a large language model is a large neural network with usually billions of parameters trained on large quantities of unlabeled text. And let's take BERT as an example, and this also applies to many more other large language models. Usually, the training takes place in 2 steps. First is the pre-training step, where the model is asked to do 2 tasks, which will help it in getting more meaningful representations of the text. Then after we get these meaningful representations, we can use it to fine-tune on downstream tasks, such as text classification. And so how exactly can large language model help to overcome some of our challenges we discovered for our chatbot? The first thing that we could do is to use a large language model to generate a data set for us. Now, during the implementation of e-mobility chatbot, I actually generated the data set manually, which is not really the type of work I would like to do, but I had to. But luckily, we now have the ChatGPT to help us. So the way it works is like you create a prompt, and you basically tell the ChatGPT, okay, so imagine you are a user who is now exploring this data set, and we also provide example questions, how many charging points did Berlin have, for example, and then we ask ChatGPT to generate 3 different but similar questions, and if we want to add conditions, we can also write it in the prompt. In this way, we get back 3 answers from ChatGPT, where the grammar is correct and it also sounds very natural. So in this way, we can generate a data set in a short time. And we can also use large language model to reduce the robotic impressions. And there are 3 different approaches, at least I can think of. So for the first approach, now we have the predefined response template. So the chatbot was always trying to answer the questions using the same structure of the response. But once we have ChatGPT, we can ask it to rephrase the predefined template. And for the second approach, we get rid of this predefined template, and we just give ChatGPT the data that we get back from the database, and we give it also the user questions. And we ask ChatGPT to generate a response on its own. And the third approach is a bit more advanced, where the ChatGPT has also to generate a SQL query and query the database, also get the data back and generate the response. So from the top to bottom, the control is less, but we have more automation in our process. I also played around myself with the first approaches, and here are the results. So for the first approach, I simply asked ChatGPT to always rephrase the text that we give it. So now if every time the user asks similar questions, we have different variations of answers from the chatbot. In this way, okay, so the user won't feel like it's kind of robotic. And I also tested the second approach where the data that we give ChatGPT is basically the questions from the user, as well as the information, which is the raw data that we get back from the database. So it is not pre-processed, and we can see all the brackets around the numbers. But surprisingly, ChatGPT can give us can extract the numbers from it and also give us the correct response. And here, it took me actually more time to create a prompt, because we know that ChatGPT was trained based on data that was until September 2021. So if a user asks a question like, how many fast charging points did Bayern have in December 2022, then ChatGPT would say, okay, I don't have the data from December 2022. So we have to explicitly tell the chatbot the information that is given to you always corresponds to the time the question asks. Also, we have to tell the chatbot, please don't mention the word information or data in your reply, because otherwise the chatbot would just say, based on the information that I get, I can say Bayern had 1,715 fast charging points. So we have to always tweak the prompt a little bit to get the correct answers. But in general, I will say the first approaches are both possible to do and also has its potentials. Also, even with the third approach, I did not try it myself, but I could imagine that it is also possible to do it, for example, using the recently very popular library like LangChain. So it has this, has this ability to generate SQL queries, actually. But one thing we have to keep in mind is that large language model is not a fix for all. And it also has its own drawbacks. because the more we trust on it, the more control we are giving away. And we sometimes also want to ensure that the quality of the response is always good. So we would need some kind of evaluation after we get in the response from the large language model. And also, in the real cases, many companies, they cannot train their own large language model, so they are always dependent on a third-party supplier. Also, we have to think about the data privacy problems. The model is just provided as an API, and it is not open sourced, so we don't have the chance to adjust models for our needs.
Okay, so we're at the end of our talk, so let me quickly sum up what you've heard about in the last 25 minutes. There is a variety of ways how chatbots can be built. One example we have shown is to classify user questions in intents using Waza, and large language models open the way for truly intelligent chatbots. Thanks.
Thank you. Nice presentation about the underhood of the chatbot. Is there some questions? There's note on Slido. Is there someone who has a question? We have some time to answer. Yes? I will rephrase after you say it for the people online.
Sure. So one of the challenges is that it's not open source, but have you experimented with open source LLMs like Alpaca and see how good it is compared to OpenAI GPT models?
So have you experimented non-closed source large language model?
Yeah, and see how
Non-open source large language model?
Have you experimented open source model, like ChatGPT, but open source versions? Not ChatGPT, but...
Okay. Not really. I mean, so far I only played around with this GPT 3.5 API.
Okay.
Yeah, but I guess like the open source models will have worse performance probably than this non-open source model.
Okay. Another one, yeah.
how is the acceptance of the chatbots among the end users?
So how was the acceptance about the chatbot from the end user?
Okay.
Do they like using chatbots or an actual input, or do they just want to see a map with the number? Or, yeah.
Okay, so do they prefer the chatbot instead of a map with the information at self-service?
Yeah, this is something we still have to do because so far I developed the chatbot and it's a prototype, and we will have to do the user test later on. And this chatbot was developed when I was writing my master's thesis, and it changed a little bit on the functionalities. At that time, what we get from the user is like the responses are more kind of robotic, so we try to fix all these issues later.
Yes. Sorry. You. Yeah.
When you try to integrate ChatGPT in different ways, how do you restrict ChatGPT to give answers only within your domain and not just some random answers on some random questions? That's one question. And how do you restrict ChatGPT to give correct answers?
Okay, so
Database.
So the question is about integrating ChatGPT into the chatbot and restricting the information to what we want for the e-mobility.
Actually, we don't let the ChatGPT to freely give us a response, but we always use it for a smaller functionality. For example, when we just give it the question and we give it the data, and we ask it to generate a response just based on these two informations. So in this way, I don't think there will be like some hallucination or kind of fancy stuff that it is not being told, but it still come up with itself.
Okay, thank you. We are running short of time. If your question is really important, you can go, but otherwise I will. So can we find the chatbot online?
Not yet, but I'm sure we will put it online. Please follow us.
Cool. Thank you. A round of applause for our presenters.